Hello ladies and gentlemen, and welcome to my probability course. I hope you will enjoy it as much as I did working on understanding all these concepts, and it seems I already have a problem, so we're just gonna skip ahead to page 2. Good. So the first problem that I think is most relevant is this one here, very simple to formulate. So we are given x1, x2, x3, xn independent samples from a Gaussian probability distribution, and we are requested to estimate the mean and the variance of the distribution. Now, before we dive into solving this problem, we should maybe understand it better. So let's say I want to measure a stick, right? So I have a stick here. No, maybe it's not too vertical the way I drew it. I'm sorry for my lack of drawing skills. And now we would like to measure it, right? So we will first measure this, let's say x1, then maybe we would measure this, x2, then maybe we would measure x3. So it's highly unlikely that we get, if we repeat the process of measuring the stick, it's highly unlikely that we will get each time the same value, because there are imperfections in our measurement system. Now, if we do not have an error into a bias error into our measurement setup, then we will probably get white noise. So if I get all these values here from my measurements and I just align them on a horizontal axis, then I will probably get, let's say, x min, x max. So I'm just aligning here the measured lengths, and then I'm starting to count, how many times I got this value, and so on and so forth. So maybe I will get something like this, and 0 and 0, right? So don't think about probabilities, just think about, I don't know, I got this value most of the times, or I got this value most of the times, although it's highly unlikely that you will get exactly this value. So start thinking about probabilities already. So this is the most likely value to get, and as I'm going away from this value in either direction, it's more and more unlikely that my measurement setup is that bad, so I fail so miserably in determining the length of the stick. Now, this is called a Gaussian distribution. And it has a mathematical formula assigned to it. We will discuss later the mathematical formula. What you need to understand in order for a function to be Gaussian distribution or a probability distribution, you need to have certain conditions fulfilled. For example, let's call this as being p of x. Right, I can have here vertical axis p of x, and I need to have p of x greater or equal to 0, right? And also I need to have the integral from minus infinity to plus infinity from p of x dx should be equal to 1. So if these two conditions are fulfilled, then I have a probability distribution, right? Now, this is white noise. This is, in practice, the distribution that any unbiased measurement of the same phenomenon usually has. But you can, certain phenomenons, they can be assigned a different probability distribution if that is indeed the case. So you have to understand that we are making this assumption. We are taking for granted this prior information about this phenomenon. So we are already guessing that our measurement is imperfect and that it will fail according to this, or it will succeed depending on what's your point of view. It will fail or succeed according to this probability distribution. So we are taking this prior information for granted. And now our problem says, okay, I have taken my measurements, x1, x2, xn, and I would like to determine this graph here. So I would like to determine which is, because this graph can be maybe, I don't know, it can be like that, it can be like that, it can have many, it can also be translated in one way or the other, so it can have many shape or forms. And the question is, okay, so tell me the mean and the variance, so tell me what this function over here is, and I will I'll be happy. Now the way to go about this, there are two ways. So you can either say, okay, I know the data, so I know x1 to xn. So knowing the data, I need to maximize the probability of the mean and the variance given this data. Right, so I need to find this and this so that the probability of this, considering the data, is maximized. However, there is also another way to go about it, which is equivalent, and this is the methodology that we will be using right now. It's okay, let's maximize the probability of the data. So let's say mu, maximum likelihood, and sigma squared, maximum likelihood, are the mean and the variance. So they are the mean of this probability distribution P of x, which is actually equal to n of x. This is the notation for a Gaussian distribution. And now, after we know this, let's maximize the probability of the data set. So okay, let's say this probability distribution had these parameters over here. Let's maximize the probability of picking the data set that we have already picked. So the probability of the data set, P data, is the product of the probabilities of each and every one event, right? Because the events are independent, so because the events are independent, then this is the probability of the data. Now, if we are trying to maximize this, you have to imagine that P of xi very small, probably small. So instead of maximizing this, we would, and you can imagine in a computer system, just multiplying a bunch of very, very small numbers, that can cause problems to the numerical representation within the computer. So that's why it is maybe better to maximize the logarithm of this probability, which is actually equal to sum from I equals 1 to n of p of xi, of logarithm from p of xi. Okay, so the question is, what is p of xi? Okay, let's remember this, that we need to maximize this. So this needs to be maximized. And let's go on to see what p of xi is. So p of xi, now we are assuming that it's the Gaussian distribution. So it's n of xi given mu maximum likelihood and sigma squared maximum likelihood, which is equal to, now this is the formula. If you don't, here is what I do to remember it. Here's a technique that I use to remember it. So I know that it has to be positive, right? So if it has to be positive, there cannot be any minuses. Then I know that it's something over square root of, there is a pi here, 2 pi sigma squared. Now this, more or less, you have to remember, you have the sigma squared, you have a pi under a root. And the thing with the pi under of a root, this is the integral of, square root of pi is the integral of e to the minus, so e to the minus x squared, integral from minus infinity to plus infinity dx. I think this is square root of pi. So if you put here an a, I think it's square root of pi divided by a. I'm pretty sure that's it. So you have to understand it comes from here, because we have an exponential function next, which if it's going, if I'm going to have an integral over the normal distribution, it has to be e to the power of minus, and then I have to have something here that will cancel itself out with 2 pi sigma squared. So I would guess it's, you have to remember this a comes under. So if it goes under and I put something under, then it goes on top and it simplifies itself with this, and in the end the pi simplifies itself with the pi, and the whole integral, for the integral from minus infinity plus infinity of p of x dx has to be 1. So everything needs to simplify itself. So if you pay attention here, it should be 2 sigma squared multiplied by xi minus sigma maximum likelihood squared. So here all the indices should be updated to maximum likelihood. So this is actually our prior assumption about our experiment, that we have eliminated all the bias measurement errors and we only have white noise within our measurements. And it's all mathematics from here. So I get this distribution and we have to minimize the sum of the logarithms. So we would be wise to look at logarithm of p of xi first, which is equal to, so the logarithm of product is sum of logarithms. So I'm just gonna go slowly here. Square root of 2 pi sigma squared maximum likelihood, plus, and of course logarithm of e to the power of something equals something minus 1 to sigma squared maximum likelihood multiplied by xi minus mu maximum likelihood squared. Okay, everything in brackets. And now I'm going to do some more logarithm push-ups, and I'm gonna go as far as saying that, well, I don't know how much we need to simplify for future calculations, so I will just say that this equals to minus logarithm from square root of 2 pi multiplied by sigma ml, which is correct, plus, it was to the power of it was this whole thingy to the power of -1, and minus comes forward. Actually, here shouldn't be plus. Actually, I can erase it, and it can be minus 1 over 2 sigma squared ml multiplied by xi minus mu ml squared. Okay, can we do some more simplifications? I don't know if it would make any sense. We should maybe perform the sum. So we are trying to minimize, once more, if you remember from page 2, we are trying to minimize the sum of the logarithms here, and sum of I equals 1 to n of logarithm of the probabilities equals with, okay, this term over here is simply multiplied by n, and this term over here, I have no dependence on I, so I can just pull this term forward, multiplied by sum from I equals to 1 to n of xi minus mu maximum likelihood squared. So it all comes down to maximizing this function, therefore I need to minimize this function multiplied with -1. So we'll do this on the next page. We need to minimize, and I'm gonna go ahead and write f of mu maximum likelihood and sigma squared maximum likelihood equals with, and I'm gonna make sure I will replace every minus with a plus, n multiplied by logarithm from square root of 2 pi multiplied by sigma plus 1 over 2 pi sigma squared ml, and I think there was no pi here. Okay, multiplied by sum from I equals 1 to n over xi minus mu maximum likelihood. Okay, now as you can see, I have here a positive term, and whatever it is in this sum, okay, oh my god, this is squared, this does not depend on sigma maximum likelihood. Therefore, if we maximize the sum we definitely maximize the whole expression. So we can actually maximize G of mu maximum likelihood equals the sum here, xi minus mu maximum likelihood squared. So we can maximize all this independently. From sigma, maximum likelihood. Okay, and this is pretty simple to maximize. You just, I mean, there are other ways. There is actually a more elegant way with inequalities, but we are just going to do it the more straightforward way, which is going to take the derivative, and I can just write over here minus 2 mu ml multiplied by sum from I equals 1 to n over xi minus mu ml. And in order to find the minimum, we need to equate this. Need to write this equation. So from both the above, it means that sum from I equals 1 to n of xi minus mu ml equals to 0, and it means that mu ml equals to sum 1 over n sum from I equals 1 to n over xi. So I remember when I first learned probabilities that they told me in school, if you are given a data set, so x1 and so on xn, then the mean of that set equals 1 over n blah blah blah. I mean, not blah blah, exactly this expression here. And my whole mathematical demonstration up to this point is the reason why. So you shouldn't just believe this. You know, you have some prior information about the probability distribution of your experiment, and then you are trying to estimate the parameters of that probability distribution so that you maximize the chance of actually getting those samples when you perform the measurement. Well, how about you know, how about the variance? Well, I'm not going to tell you the formula that they taught you in school about, but actually I'm going to tell you. So they taught you in school, so go, that the variance should be 1 over n sum over I equals 1 to n from xi minus mu xi minus mu squared. So this is what they taught you in school. Okay, so is this a good estimate? Well, I'm going to tell you that it is not. So if you bear with me in the next course, in the next lesson, I will show you why it is not a good estimate. Thanks for watching, everybody, and I will see you in the next course.